I decided to make a list of considerations that must be taken into account when designing a VTOL aircraft. So I'm not going to go through by order, but one of the most important considerations is the drivetrain mass. So it would be the power density of the actual drivetrain, not the propulsion system. The drivetrain. So getting power from a centralized power plant to multiple props located a significant distance away. So gearbox shafts, conventional systems, are going to weigh around 0.3 pounds per horsepower. That's going to be your main reduction gearbox on a rotorcraft. Now that includes a significant amount of reduction. If you're talking just a bevel gearbox for a rotorcraft drive shaft, I'm talking like 0.15 pounds per horsepower, half of that. An electric motor, for an electric motor and a generator, if you take the Honeywell 1 megawatt generator and axial flux motors from magnets, the highest power density available, you're looking at 0.6 pounds per horsepower minimum. So, and again, I'm comparing a main rotorcraft gearbox here. It's not a comparison of a non-reduction gearbox. Drive shafts, of course, made of carbon fiber, are very light. Going back up here, we have propulsive efficiency, so mass times velocity. Velocity is going to be your main determining factor in how much energy you need to create that lift. Moving a large mass of air at a low velocity is much more efficient than moving a small mass of air at a high velocity. So having the prop tips at the speed of in the Mach range would be it results in vortices. It results in a significant amount of noise being generated. Control stability in the absence of MEMS gyros. So we know if they measure capacitance. They use a Coriolis effect to transfer rotary motion to linear motion, then use capacitance. Convert that capacitance frequency number into a number that can be interpreted by a CPU and then performs the necessary control input. These kinds of gyros are very accurate and very cheap, but they're nonetheless a computerized system that's relying on sensors, and in the absence of that system, flying the aircraft by hand is impossible. We're talking about these multi-prop rotor systems. Structural efficiency, so if you decentralize that mass over a large number of rotor discs, you're adding structural weight to connect all of these props together. That's going to, of course, add weight. The acoustic signature is an improvement in the type of sound, not the magnitude of the sound. So it's changing the sound from an oscillating sound from a main rotor blade thumping sound into a continuous drone, but the raw decibel output is equal. Crashworthiness is going to be impeded by a reduction in the EW-GW ratio, or I should say an increase in the empty weight thrust ratio. So essentially you're consuming all of your weight on a heavier powertrain, heavier drivetrain. Loss of auto rotation potential. I'm not big into auto rotation. I don't really believe it's very useful, because when you're doing your UAM type flights in a conventional aircraft flying in urban areas, you're not going to be able to take advantage of auto rotation because you're going to be in the gray zone. So failure of rotorcraft to deliver in UAM is not due to inherent design reasons. So you can argue, well, why don't we use helicopters for commuting right now? The answer is the costs and the lack of infrastructure, and you can add noise on top of that. And this is one of the most important, I would say, of the 9 reasons or 9 considerations to take into account, because if you're going to move a mass of air, you're going to generate a certain decibel output. A rotorcraft is around 115 decibels right outside of the aircraft. It's 115 decibels. But energy density propulsion system, I skipped over this in the beginning because it's so obvious that lithium system is going to have. I mean, if you take kerosene is 43 megajoules a kilogram, you multiply that by 25%, so your brake thermal efficiency of a small turbo shaft. Well, you're still looking at you have 42.8 megajoules times 0.27 per kilowatts. It's 11.55 kilowatts times 25%. Times 2,000, you're looking at about 5,800 watt hours. You're looking at around 24 times more energy density than a lithium system. So very unrealistic. And aside from that, to summarize, I want to say that there is zero advantage to going to these kinds of architectures. And you might ask, what am I talking about as far as unconventional architecture? Well, you can think of Uber urban air mobility. We're talking about these types of aircraft. There's just really no major killer advantage to going with this type of aircraft over a conventional helicopter. So I have a unique opinion, and that is, if Silicon Valley is going to do something, they have to be innovative. And rotorcraft are old technology. It's been around for nearly 100 years. So you can't exactly bring a helicopter and build a heliport and say, oh, this is some new innovative thing. If they want to raise money, they have to have some kind of innovative aspect to it. But of course, innovating for the sake of innovating is sort of pointless. Conventional rotorcraft with vertical embark technology allows you to basically pick up or drop off your passengers anywhere, provided there's a small 5 foot by 5 foot area. You don't need to land a primary craft. So that's what I would focus on. I would take the conventional rotorcraft, try to improve it as much as possible, rather than radically changing the fundamental aircraft architecture away from the stable, reliable, proven single main rotor system. So that's my opinion.